My name is Akshay Atavale and today I'll present DarSwin distortion-aware radial swin transformer. Consider this 360-degree panoramic image and let's say you want to capture this wide scene using a single camera. You can do this very efficiently using a wide-angle lens. But this efficiency comes at a cost of distortion as seen by the distorted tower here. Along with the distortion, different lenses can produce different types of distortion depending on their characteristics. To understand the distortions in these images, we'll need a lot of training images from each lens. Therefore, in this work, we present a network that is trained on a certain type of lens and can be used to generalize without fine-tuning on other type of lens that is not present in the training data. To achieve this, we use Swin transformer as our base network, but we move away from the traditional Cartesian partitions and adapt polar partitions considering the radial nature of distortions. Along with the polar partitions, we use the physical characteristics of the lens, which is defined by a radius and an angle curve. Consider a ray hitting the camera at an angle theta I and projecting an image at a distance Ri. We use these two values to plot our radius and angle curve, which in turn is used to sample the radial values for our polar partitions. So, if the lens changes, we can adapt our network structure to the given lens's distortion. Using these two modifications, we evolve the Swin transformer network and present DarSwin, a distortion-aware radial Swin transformer network that has the ability to adapt to unseen lenses at test time. Now that we have our polar patches, we use a sampling layer to embed these patches. Due to the polar partition, the number of pixels in each patch is different. Hence, we use sampling where we sample same number of points from each patch to make the embedding similar. In this example, we show 9 sample points per patch and we sample accordingly to keep the orientation of the patch intact. We use bilinear sampling to define the patches into polar format, and we use this polar format to linearly embed these patches using an MLP. After obtaining these embeddings for each patch, we feed it into a Swin transformer block to perform local attention. And since we use polar patches, we define angular relative positional encoding for these polar patches. This positional encoding is defined differently along the azimuth and radial axis. Along the azimuth axis, we calculate the relative phi value of each patch with respect to every other patch and define a B-phi matrix. For positions along radius, we take the help of the radius and angle curve, where instead of defining a relative radius values, we define relative theta values and calculate a matrix B theta. We use these two matrices in our attention equation to define angular relative positional encoding. Now to prove this theory, we do classification experiment on synthetically distorted ImageNet with radial distortion. We use spherical distortion as it has only one distortion parameters that can be used to define different levels of distortions. As you can see, here we define 4 levels of distortion from very low to high distortion, which are mutually exclusive. This helps us to define 4 different training sets which we train our network on, and then we test our network on all the value from 0 to 1 to understand the generalization capability of our network. We plot an accuracy versus distortion curve and we train our network on the low distorted images. As you can see, the baselines degrades in performance as we move away from the training distortion. But our network DarSwin outperforms the baseline in generalization to lenses which are not present in the training distortion. To make the comparisons fair, we give the lens information to the Swin transformer network in the form of undistortion. But as we can see, the Swin network trained on undistorted images still degrades in performance as we move away from the distortion region. This happens due to the artifacts caused by the undistorted images as seen here. Please refer to the paper for more results with different training distortion levels. Thank you.